As a writer, I go through a lot of toner cartridges on my printer. Some printer manufacturers have lowered the price on the physical printer itself. Why? They've adopted a razor blade model. You know, I'll sell you a cheap handle, then ask you to buy my proprietary blades every month thereafter, as long as you own that inexpensive handle. Same with printer companies. Some have gone so far as to put chips in their toner cartridges. One, they say, is to alert you when the toner is about to run out. And two, it's to rule out that you're using non-proprietary cartridges. You know, those knockoff toner cartridges, they just won't work in this printer. Now, I'm fortunate in that the make and model of my printer doesn't go through that. I could use a knockoff toner cartridge, but I'm actually pretty loyal to the brand, and I'll continue to buy from that vendor. All right, how does this relate to anything? Well, my guest this episode told me about a hacked printer cartridge chip. Naturally, I was curious. Why would somebody invest the time and money into hacking something so common and seemingly minor? Then my guest presented a chilling scenario. Imagine you're a nonprofit in a war-torn country and somebody generously offers you inexpensive printers. You'd probably take them. But now you're beholden to them to supply toner cartridges, which all have been compromised. This creates an office-supplied attack. From the compromised toner cartridge, attackers could infiltrate your network and phone home to download dangerous payloads onto your system. Ingenious, right? And it doesn't stop there. My guest has gone even further with his silicon hacking, taking on challenges like cracking the security of a Raspberry Pi. Stick around to hear more about his work and the growing threats of hardware security that many people overlook. This is a story about the hacking of embedded silicon within common objects in our day-to-day lives and how it's becoming more common and what the consequences of this lack of security might mean. I'm Robert Vamosi. This is Error Code.
Hi, I am Tony Moor. I am the Senior Director of Silicon Lab Services for IOActive. IOActive is a full-stack security company, and we provide services all the way up from humans down to transistor level.
Back in episode 3 of Error Code, I interviewed Joe Gran, who I consider to be an early pioneer of hardware hacking. I don't get a chance to meet as many hardcore hardware hackers as I'd like. And by hardcore, I mean people who live and breathe embedded security. So I asked Tony, how did he get involved in the space?
Yeah, I started off always working in labs. About 20 years ago, I had the great opportunity to get into semiconductors, and I worked in a failure analysis laboratory for a major manufacturer, an American manufacturer of chips. That gave me a good background into the physics, what a chip is composed of, how to prepare them, deprocess them. And since then, really, I've been working in security, either on the hacking side or the testing side ever since then. So really, for 20 years, I've been working at transistor level with silicon devices.
For the past 20 years, the focus in cybersecurity has mostly been on software vulnerabilities, with hardware risks being overlooked. I'm curious, did Tony ever feel like he was working in a niche area, or were there actually more things being done in hardware vulnerabilities than most people realize?
I think that's right. I think it's becoming, even now we have not a problem, but it's a challenge to make people aware of these vulnerabilities that can happen at the hardware and at the semiconductor layer. I know that these attacks have been taking place for 25, 30 years. We're back in pay TV times when platforms were being opened up and you could buy the counterfeit cards to fit your pay TV box, your Sky or Canal Plus, depending on which country you were living in. I was involved in some hacking of devices maybe 15 to 20 years ago. So at least I was aware of these attacks and these vulnerabilities and this kind of sort of industry which was going on. But even now, I think all manufacturers are aware of these threats, but when it comes to integrators, maybe they're not so prepared and they're not so aware of what can happen on a real hardware. I mean, really at the silicon level.
Unlike software hacking, there's a pretty hefty price tag, a cost entry, to start hacking hardware. Has that changed much over 20 years? Or does it become less costly to get involved in hardware hacking today?
Absolutely. You can definitely see that across the board. When we're talking about hardware hacking, we can talk about three main levels. Uh, on a component level, we're talking about either a non-invasive, a semi-invasive, or a fully invasive attack.
Right. So there are different layers of hardware hacking, and we're going to explain those. So, non invasive, what's that?
A non-invasive attack comprises things like voltage glitching, voltage monitoring, things like this. This is where you have access to the device, but you're only influenced from the outside. So you hook up probes, even use electromagnetic effects to try and influence inside of the package what's going on there while the chip is running. So this is a fairly, it's not a new set of techniques. It's been around again, decades probably, but the level of entry, the bar of entry to get running on those attacks, it's very low now, and that's been quite a sharp reduction over the sort of the last 10 years. There's been a lot of kits that are offered almost for hobbyists to kind of an educated hobbyist can get up and running for a few $100 really on their bench and try and hack some of the chips in that kind of realm. So we're talking, voltage regulators, oscilloscopes, things like this. So it's basic electronics components. Um,
And then there's semi invasive.
The next stage up from that being semi-invasive, that means that we have to get access to the dye inside of the package. So that is a different level. So you have to use chemicals for that. What you do is you'd open up the top of the device so you can actually get a laser, for example, inside and onto the semiconductor device itself. Now, the programming and how this works is very similar to the non-invasive. You're trying to introduce a glitch or monitor something, but with a laser, you can be much more accurate, but you do need access to the die itself.
And of course, there's destructive or invasive.
The most invasive techniques is more what my interest is, and in this scenario, you have access to the die, and you have the ability to physically change the chip itself. You usually do some kind of destructive deprocessing to learn about the components within the silicon, and then you use that information, you analyze that, and then you kind of compose an attack where you physically invade the chip and alter its functionality or access some buried data bus deep within the chip, for example. So, non-invasive, hundreds of dollars just to get started and some motivation, of course. Semi-invasive, you're talking, hundreds of thousands, and fully invasive, you could be talking millions, really, depending on the levels you need to go to.
So I'm curious, back in the day when he was hacking pay services, was Tony doing a non-invasive attack, or was he actually getting into the chip itself?
Yeah, these are fully invasive attacks, which has been my sort of main interest over the last 2 decades. So you can talk about platforms like Pay TV, Printer Ink is another very good example. Video game accessories. These are three kind of real, the biggest areas where there's the most value in creating or finding a vulnerability in the hardware itself. For example, if you're in the business of making printers, you want to keep that printer ink market to yourself, of course, and that's why they put these authentication chips on the ink cartridge themselves. It might be a $20 ink cartridge, but there might be like a couple of dollars worth of ink there. But if you put that 50-cent authentication device on there, that's going to really stop a lot of people from making compatible ink for your platform. So it's like the razor handle and the razor blade kind of concept. You put the printers out there at quite a low value, And that is very similar to the video game market as well. The video games systems are sold, very little profit uh, in there, but they know that the games and the accessories will bring the revenue. You just want to get that hardware out there in the market, and then they will make the money from the accessories. So that's three good examples of where you have a kind of a service or a system, and you create a lot of most of the revenue by selling accessories or software for the platform.
Let's break this down a bit. Suppose you're looking at a printer cartridge, something that seems relatively low cost and straightforward. Why would somebody go through the effort of performing a destructive research on the chip inside, especially when the financial reward might not seem to be as high? Is there any real incentive for someone to invest the time and resources into hacking such a commodity?
Manufacturers try to guard against all of these things, really, but if you have the motivation and there is a reward there, then you have to kind of accept that at some point your platform is going to get hacked. Because if you want to make compatible printer ink, this could be multi-billion-dollar business, and it is for some of the large, the very popular platforms. Um, you don't want to certainly bring a product into the marketplace which is susceptible to a basic glitching attack, which could, be done by somebody with a few $100 or a few $1,000 of equipment and a bit of motivation. That means that, within weeks or months of the product being launched, that's going to be compromised, and the manufacturer, the OEM, they're going to have their revenue taken away from them. Somebody's taking their lunch money pretty much immediately. But if you bring out something which is much more protected to the point where somebody will have to perform an invasive attack, a fully invasive attack, that would make, hundreds of thousands of dollars and many, many months, hopefully years, until somebody creates a compatible clone or some kind of compatible product, which would then affect their revenue. So it's a matter of time. Manufacturers want to have something in the marketplace which will last as long as possible. But really, there's nothing you can do really to make something that's completely unhackable.
I was discussing the potential for nation states to counterfeit chips and how that could disrupt economies. Where does Tony think these counterfeit chips are most likely to be found? Are we talking about sectors like automotive or durable goods? We mentioned printer ink earlier, which honestly never crossed my mind as an attack vector. What other areas might there be?
It could be absolutely anything, to be honest with you. I mean, we've worked on a lot of material for marketing purposes, just for the awareness, and these devices are going into absolutely everything. Like a car will have hundreds of devices in now, and it must be a nightmare to verify the origin of all these devices. And of course, financially, people are keen to find the most effective and efficient way to source these products. And you have resellers, you have distributors. It's a real maze. But if you have, and there's many cases where you've had someone working, buying chips from China and then implement them, bringing them in through the supply chain via another country, through a sort of backdoor. So then you can't trust that supply. You have the relationship between Taiwan and China, of course. So, Taiwan is really responsible for a huge amount of semiconductor manufacturing. It's unreal. And there's, of course, a great interest from China for this as we kind of develop and become more reliant on these devices and these products that we're buying and living our lives on. Um, Certainly, there's a push for Europe and the United States to bring that production back home. But in the meantime, we still have a huge reliance on the Far East for supply of semiconductors. The problem that Europe and the USA have is probably going to be the lack of experts, engineers. We don't naturally have that amount of high tech jobs or high tech careers. So you may be able to spend the money, build the fabs, make the designs, but then you need people to operate in these fabs, these engineers, process engineers, development engineers, um, integrators. There's a lot of jobs that need to be filled, and they don't exist already. if you know what I mean. So it's I think there's a bit of a worldwide lack of really high-end engineering uh, expertise.
Years ago, I was introduced to a side channel attack on a payment processing system where voltage fluctuations were analyzed to exact card and chip data. I'm curious, what other types of small-scale hardware attacks like that might we be overlooking? In other words, how do hardware attacks compare to software-based ones in terms of complexity and scope?
Again, yeah, I mean, you're talking about a non-invasive glitch or something. It's not a glitch, actually. What you're talking about, it's a voltage analysis. Chips need some kind of power consumption for various functions, of course. And if you inside a chip, you have generally some flash memory in there. So flash memory takes a reasonably large current to kind of write those values into a memory. Therefore, you can monitor the power consumption and you can deduce kind of what is happening at certain moments in time, and that's how these things are usually done. Certainly, when it comes to a fully invasive attack, we're talking more about a good level of reverse engineering. You could class a side channel attack as more like an opportunistic. You start off at a very high level. You kind of scan around, you're looking for something, and then you focus down, and then maybe you'll find something that's of interest. When you commit to something that's fully invasive, you have to devote a lot of time to really physically understand the composition of the device physically, the layers, the functionality which is embedded in that device, where the memories are and things like this, where the inputs, outputs, and all of the transport happens. It's really it's quite an involved process, but at the same time, fully invasive work, it's almost like you can't fail if you have the motivation and the time and the money. Um, a chip is just transistors, really, at the end of the day. There's some analog functionality, of course, but the digital element, which is where all the computation is taking place and all the secrets are being transferred, this is all embedded in transistors. And if you have the power to reverse engineer, deprocess, and understand these transistors, then you can extract that functionality essentially. It's like trying to hide a component of a car that you've designed. You have to know what is where and it's all functionality at the end. You can obfuscate to a point, but really these transistors have to work for the chip to work. So therefore, if physically you will find them.
So, what is the threat to an organization by hardware hacking? What do organizations need to be thinking about today that they weren't thinking about 10 years ago?
Free printers, for example, this is a good one, and it's quite relevant to what I've just been speaking about. And what they did was they installed the printer, installed it to the network, of course, and then they were supplied with some cartridges, which then kind of loaded some malicious code, somehow got into their network, and then infiltrated and extracted some information from that company. Not sure whether it was a government organization or whether it was a private organization, but that's the sort of thing. It was a kind of a cloned cartridge. But instead of the flash being loaded with something legitimate, it was like a Trojan, and that's the way they got into the organization's network.
So, here, office supplies become a literal supply chain attack.
Absolutely, yeah. I mean, it's usually these chips are very relatively simple. They have a small amount of memory, but it depends how much, you can, if you're an expert, you can keep your code very discreet and small and load it onto a very simple device, and it can be enough to do some damage.
So that makes sense to me that someone would put the time and effort into something like that because they could exploit it in a number of different organizations later.
Absolutely. Yeah. I mean, we're talking about security, but it could be securing, physical security. It could be securing a company's revenue, like in the printer cartridges or the video game accessories, or it could be, some kind of physical, safety. Somebody's at risk because of this, because of some malicious actor that's, has access to a company or a building.
I know that chip manufacturers are putting in some sort of trust to ensure that the chips are not vulnerable to outside attack. How difficult is it for Tony to get around something like that? Or is it not possible to get around that?
It's always possible. The most basic and mo most obvious example of an anti-tamper measure is an active shield. So if you see a chip with an active shield on, you know it's hiding something pretty interesting. So an active shield is basically just a grid of lines that cover the chip, but these are sensed. So maybe a group of four, maybe a group of eight lines, and a signal is sent across those lines, across the entire chip, from the moment that it's powered up until the moment it's powered down. Now these signals have to match to for the chip to be able to work. If one of those lines is broken or the timings don't match, then the chip will sense that and it will erase its flash. So the firmware is gone, everything interesting inside the chip is gone. So one of the valid things that we can do is test to see if these countermeasures are effective or actually implemented or not. Maybe it's a shield which just isn't sensed. It just looks like a countermeasure, but we can make a cut and then we can power the chip back up and see how it reacts and see if it's done its job correctly. There are many, many other anti-tamper measures and protections that manufacturers put on chips, and they all obviously listed in the data sheets. But as to how effective they are, that's kind of open for more discussion, I would say.
It's fascinating that a device could claim to have anti-tamper features, like light sensors that shut down when it's exposed to light. Yet if it's not actually functioning, it's essentially useless. Has Tony encountered situations where these supposed security features don't work as intended? And how does that impact their effectiveness?
I've seen examples of devices that have claimed to have like a light sensor, for example. So as soon as you take the chip out of the package, it's exposed to light. It would sense that when it's powered up, and then it would shut down. We found that it just didn't work. You know, we were careful to begin with. We keep it in a box and we power it up, but then we just tried one time with without any protection, and it just it didn't care. So it's one of those things. It could be a good selling point. People think it's quite a cool thing. Oh, that's an extra layer of security, but there's no point if it doesn't work.
I used to work in an EDA software company, and I know a lot of effort goes into modeling the chips before they even go to the fab. It's surprising to me that someone at the fab could still alter the chip before it's physically produced. How common is such alterations likely to happen at the foundry level, especially when dealing with large players like TSMC, who manufacture a significant portion of the world's chips?
Well, exactly. I mean, we talk about, say, the foundries like TSMC, for example. They're making probably half the chips on the planet, right? But somebody else is there. They're not necessarily developing IP. In fact, most of the chip makers aren't. Yeah, some of them aren't not developing their own IP. They will kind of buy IP from IP providers, and they will combine it with their own designs and their own specific requirements. And that final design will be given to TSMC, and they will just fab it and as much as you want. TSMC obviously have to test that output, but as long as it works and it functions, then that's what they're being asked to do. It's almost like comparing it to a printer. The printer isn't writing the content. It's a journalist writing the content that gets sent to the printer. They print it out. As long as the print is kind of correct and it looks of a good quality, that's all the printer cares about. They're not really analyzing the content and checking for grammar.
Tony mentioned the possibility of vulnerabilities being introduced during the foundry process. How common is it for vulnerabilities to already exist in the hardware when it's manufactured and then later get exploited? Are there known cases where these vulnerabilities were built into the chips from the start? Or is it more about discovering them after the fact?
I've not personally, but there has been some examples, and that there are some very small examples, like a while ago on a laptop, there was found to be a passive component, but it was actually an IC. It was a very small device, and it was camouflaged as a capacitor or something like this. So that kind of makes you think, how far do you have to look? How deep do you have to look to discover this kind of infiltration? Because an integrated circuit could be less than 1 millimeter squared. And that is easily small enough to be packaged as quite a small capacitor or a resistor or something that looks fairly innocuous. and you know how complicated devices are these days. Yeah, it's a big task to be checking every single component on a laptop, for example, or even a phone.
So this gets into the importance of having supply chains penetration test their chips as well.
That's a very good point. That's another. I'd say the three main targets for our work at the silicon level is, I mean, the first one is penetration testing. So we take a device of a manufacturer and we test that it's resistant to certain attacks, non-invasive and fully invasive, and everything in between. The second thing we can do is inspect, analyze supply chains for any kind of malicious devices, any non-standard or clone devices, anything that's been tampered with or replaced. And this is something we see more and more of. It can be something very basic, like a chip has been relabeled to signify a higher memory content, for example, and somebody just wants to take a cheaper product, relabel it as a slightly more expensive product, and make like 2 cents per chip. This is a very basic level, so it's not really it's nothing super malicious. It just may not work for its particular application. But if you get deeper and deeper, if you're kind of a nation state, imagine if you have access to a design of a device and you had somebody within the fab that could access that design and then add functionality to it. That would be like, we class that as a hardware Trojan. So the device would, on the face of things, it would behave the same. There would be no performance difference, but there's added functionality there which could allow somebody to access it in the field. This would be really at the most difficult, end of the spectrum. And you have to ask yourself who would be able to kind of detect that difference if the device operates exactly the same. It just so happens that there's been 50 or 100 transistors added, a very small amount of functionality. We're talking about something that could contain billions of transistors. Then who's going to check for that? Because it's almost invisible. But that's the kind of thing that we do, because if you have to, if somebody adds transistors or removes transistors or changes the design, then we can see it physically.
So we've talked about printer ink, and we've talked about potential for supply chains to be hacked. Are there other areas of attack that we're seeing in hardware hacking that's interesting?
Yeah, it's interesting to maybe add a little bit about the other things that we do. If we have I mean, we are very lucky. We have great experts, and we have all the tools and the toys in the labs to do all this cool work. And when you start to think about being able to extract functionality at transistor level and do all this analysis, it's a very, very, very powerful tool, I think. You can really extract the complete functionality from a chip and export that into a design file, for example. So that's very important for comparing a design. The manufacturer gives us a perfect sample, and that's their design. That's a known good design. We can compare the suspect design to that. We can literally extract the design file. I mean, it's an amount of work, but it can be done. If we can do that, we can also examine for IP theft. If there's some functionality that's been implemented into a chip that is not licensed by the IP owner, for example, we can compare for that. Even if it's a physical structure or a process that's been implemented into a device, this can also be analyzed by us, and we can either support somebody who's being sued, or the other way around equally. It can be, it doesn't have to be an intentional, it can be quite an accident. It could be some kind of technology that's been implemented into a device that somebody just wasn't aware that somebody else owned. But this is really a kind of a legal merry-go-round, which is never ending. And people need experts like us to be able to provide this, this evidence to defend themselves, or to make a legitimate claim against somebody.
So getting back to the cost of entry here, there's a lot of money to make a chip. So if somebody were to make a fraudulent clone of a chip, we're still talking about a lot of money invested up front. It's not conceivable, or is it becoming more conceivable, that you could flood the market with these false chips at some point?
Yeah, I mean, of course, if you want to make a legitimate product, so you're not just like copying, you can clone a product, clone a chip, So it's a non-OEM device, and you've just copied that. Um, yeah, it does cost money, of course, to make the design, to make the masks for that process, but it's as long as it's not sort of a cutting edge tech, it's not going to cost that too much. If you're developing a compatible product for ink or video game accessories, then it's there's enough reward there to pay for all this design work and these masks that are required. Um, you can potentially put a solution in something which is already in existence, like an off-the-shelf IC, which is probably not going to be as secure. If you're the first company to come up with a compatible solution for a major ink manufacturer, you don't really want to put your solution in a non-secure device also, because then that opens up to even further people. Then it's a race to the bottom. Then you don't retain that value. So if you're the kind of the one that supplies the magic solution, really it's worth your time to implement that properly in an ASIC, which is secure and is going to keep your IP secure and not open it up to the rest of the market.
So, separating out the physical part of the chip, there's a lot of IP in the firmware. And so you'd want to take that physical chip, but you'd maybe want to just change the firmware and put in something else.
No, I think that's right. I mean, if you want to hack a chip, that's really what you want. You want the firmware, and that's going to be in the flash. Generally speaking, you'll have um, some memory like a non-volatile memory like a ROM, which will just get the chip alive. Will just allow it to boot and function. But then, really, the good stuff is going to be in the flash. And so you have the firmware for the device and the system. So if you can get that out, you've got everything that you need, and yeah, you can change that as much as you want. To a point, of course, still has to work. You can disguise it, but I suppose if that firmware still contains IP from the OEM, then you're still kind of breaking the law by using that.
Tony's participated in bug bounties. This is a program where a company will put the money up front and say, hey, if you can break into this chip, we'll pay you a certain amount of money. And so in this case, it was a Raspberry Pi.
We decided to take the challenge offered by Raspberry Pi. It was a bug bounty, so it was a race to extract some key material from some one-time programmable memory. Um, One-time programmable memory can be kind of various things, so we had to do a little bit of research, and we found it to be an anti-fuse array. So we did a bit of destructive analysis to tone the chip down, and we identified where these anti-fuse values were, and we kind of reconstructed the memory so we could work out roughly how it worked. And we used a technique called passive voltage contrast. So that's when you use a focused ion beam to as an imaging technique. With a focused ion beam, if there is a conductive material which is grounded, it will glow very brightly, in fact. But if it's not grounded, that conductive material will just appear as an insulator or anything else. There is really no material contrast in a focused ion beam image. It's really kind of all looks the same. As soon as you see something that's grounded, it lights up almost like a light bulb. And we found that if we deprocess to the right point, we could actually image over this array of fuses, and they would just light up as ones and zeros. A white dot would be a one, and a nothing would be a zero. So we worked out we had to reverse engineer the entire memory array to work out how it is addressed, and then work out where this special address would be. That Raspberry Pi would hide this secret, this challenge. But by the time we did all that, and then told them where this secret address was, they were quite happy, and they just let's have the bug bounty reward instead of sending us the special sample with the special key that we'd have to extract. They were that convinced that we could do it, they didn't bother sending us a special sample. So this was like a very cool thing to discover, because up till this point, fuse and anti-fuse, well, specifically anti-fuse, was seen as really impossible to read physically, and we proved that it was possible.
This may be a good time to get some color around what that destructive process looks like in hardware hacking. I'm familiar with taking the resin off and stripping down layer by layer. Is that what we're talking about?
It is absolutely, yeah. So you sound like you have some good experience there, but that is really what we had to do. We had to take the chip out of the package first, and that involves some acids. So we dissolve the epoxy package, and then we end up with this nice, clean, shiny piece of silicon. Of course, that's made up of many, many layers of circuitry. In this case, it was 8 metal layers. In this occasion, we used a mechanical deprocessing technique, which is basically just polishing, or CMP, like a chemical mechanical polishing, like what they use in the fabs to make the chips. We use a very small setup for this, and a very small jig that we kind of adjust, and then we remove layers with a diamond abrasive until we get down to the layer we want, and then we stop. And that was pretty much it. But it takes some skill. It takes some experience to do this kind of things, but mechanical polishing is probably the most basic form of deprocessing you can do. It's very nice because everything is flat. It removes material, all kinds of material at the same rate. It doesn't really prefer any particular material, whether it's a conductor or insulator. The surface at the end is flat, which also helps us a lot. We do much more complicated techniques to deprocess, like ion beam mills. You can even use the focused ion beam to delayer. We use wet chemicals, dry chemicals like plasma etchers, things like this. But usually with mechanical polish, you can get something, get some kind of result. And in this case, it was possible.
Tony mentioned layers, so I'm thinking it's kind of like a sandwich.
Absolutely, yeah. I kind of describe it as a layer cake. You can almost imagine it as like a multi-layer PCB. So you have just a lot of layers of transport, and they're kind of embedded in an insulator material. So it's all conductive inside the chip. These days it's copper. It used to be more aluminum, but these days it's more copper circuitry. So they're kind of sandwiched together with insulator layers between them to separate them, of course. Uh, Difference between PCB and a chip is that at the bottom of the chip you have the actual functionality as well. So you have, whereas a PCB is just really for transport. There's nothing, it's not doing any computation. It's the components that are doing the computation. In a chip, you have all this crisscross transport of the layers and of power. But then at the very base of the chip, you have the actual transistors which are switching off and on. So one zeros, and they're kind of, transistors being the actual building blocks of of the of the industry as a whole, really.
So let's say you're looking at a black box chip. You have no idea what it does, and you're starting out. You're starting to shave layer by layer, and then you test that layer to see what's going on inside, and you decide this isn't very interesting. So you move on to the next layer and the next layer until you find the interesting part.
This is correct. Yeah, we start at the top usually because it's the one that's looking at you. So the top is usually not very interesting. It's just a grid of power distribution and ground. You have the bond pads, which is, of course, how the chip is connected to the outside world and the package. So generally in the top layer, there's not that much going on, but we image it just for reference, for navigation purposes, because who knows if we have to perform an invasive attack, we will start off with a fully processed chip, and we'll have to use some features on the surface to navigate from. So say a bond pad, for example, but otherwise there's not really that much of interest. It's just really power and ground distribution. Once you remove that layer, there may be a second layer of power and ground distribution, but generally the further down you go, the more interesting it gets. So if you start from the bottom, you could say, okay, we have the transistors, and these are then linked on the first metal up, and these are the kind of the inter logic cell connections within the device. So within the CPU, for example, you'll have a bunch of transistors, and if you hook them up correctly, you'll make a logic function. So okay, this one's got 10 transistors. It's a NOR gate, and this is what the logic cell is doing. So you have internal connections to make this NOR gate, and then you have obviously many thousands of these gates and other kinds of gates, many different designs of logic cells, and they are all hooked up on the layers above that. So generally, you have one set of transport that goes in one direction, and then the X direction, for example, and then the layer above that will go in the opposite direction, and then you have connections between these metal layers, like kind of, it's almost like a huge motorway network with like multiple layers, like a huge flyover or something. But then you have kind of connections in between the lines as well, so the signals can get up and down and kind of get. So they're very, very efficient, optimized circuits to get signals transported around the chip as effectively and as efficiently as they can.
So I'm curious, how long does it take Tony to go through this process? I mean, every chip is different, of course, but on average, is it a relatively quick process, or are we talking days and days and days before he actually can get to the analysis?
Yeah, it's a long process. You have to perform. I mean, you could start off. You could deprocess one sample, and you may get a layer of. You may deprocess to an area of interest, a layer of interest, which is good enough to image. You may have to take 1,000 images of that layer in the SEM, the electron microscope, or you could take 10,000. Who knows? Or it could be 50. It just depends on the complexity and the size of the technology and how big the chip is. And then you have to go layer by layer down. So you're talking many weeks, more like months to get everything that you need from the device imported into some special software that you need to deal with that amount of data. And then the software will allow you to kind of combine the images, make this jigsaw from all these individual images, stack these layers on top of each other, and then annotate all these layers of circuitry. And then the software will help you export a netlist from those images, and that netlist is the functionality of the chip. And then you have to perform some quality control, of course, make sure there's no errors because we're taking images of real things, right? There can be scratches and debris and things like this. Then eventually you filter the netlist, and then you come up with you know you find out where the interesting parts of the CPU are. What is performing the decryption, for example. That would be something interesting that an attacker would want to find. And encryption will be synonymous with certain logic functions. So therefore, an attacker would say, okay, it's an 8-bit processor. We're looking for 8 XOR, cells or something like that. And then they will kind of filter, they will search around this functionality for examples of those features, and that will give them a clue as to where to look next.
So speaking of that, is Tony finding that there are opportunities to speak at conferences about hardware hacking? Is there more of an awareness today at conferences, or is this still a niche area?
No, it is. We feel it's something that, I mean, we work on this a lot as well. We're very hard to illustrate these attacks, because for a very long time, a fully invasive attack has just been regarded as a residual threat. But then side channel, so was that maybe 15 years ago, but it's really not now. And like we said at the outset, there is different bars of entry for each type of attack, or each kind of group of attacks. But even on the fully invasive, this is coming down. We published some recent research on Raspberry Pi, which is very interesting. And we used our equipment to do that, which is quite expensive, of course. But we also illustrated that it's relatively easy for somebody to rent access onto a scanning electron microscope or focused ion beam, something like this, something that's hundreds of thousands of dollars to buy. $50,000 a year to maintain minimum, could be a couple of $1 million to buy, but almost all universities will have one. They will have a material science department or a computer science laboratory, and they will have SEMs and focused ion beams and things like this. And typically it's $100 to $200 per hour to rent. You can operate it yourself if they trust you, or you can get one of the technicians or engineers in the university to operate it for you. So certainly I've seen these systems become a lot more prevalent in universities and academia, a lot more easy to get a hold of and access, like exist already, if you know what I mean. So it's I think there's a bit of a worldwide lack of really high-end engineering.
I'd like to thank Tony for coming on the show and talking about hardware hacking. Our conversation delves deep into the evolving risks in hardware and supply chain security, from small-scale attacks on these printer cartridges to broader vulnerabilities in devices that we rely on day to day. It highlights the constant challenge that manufacturers face, protecting their devices from such attacks while staying competitive in the market. And we explored how invasive and non-invasive attacks can be used to exploit products and systems, leading to potential data theft and larger security threats. So, whether it's a compromised toner cartridge or just a hacked chip in general, this episode reveals how vulnerable our seemingly innocuous technology really is. Hey, if you're enjoying Error Code, tell a friend. I'm sure there are other people out there who like narrative information security podcasts. And I'd really like to hear from you. Go to errorcodepodcast.com to get more details. And tell me what you like, and even what you don't. I've got some great episodes coming up, including more on hacking water facilities. Subscribe today. I don't want you to miss out.